All right, let's get started. So, hi everyone. Welcome to session 4A, PIM Accelerators. I'm Jongse Park, an associate professor from KAIST. Today we have 5 papers in the session. I'm pleased to introduce our first paper titled PreSto on in-storage data processing system for training recommendation models. The speaker is Hye-Sung Kim, a master's student at KAIST, working with Professor Min-Soo Liu. His current research focuses on hardware-software co-design and system architecture for ML application. Hye-Sung, please take over from me.
Hello, everyone. I'm Hye-Sung Kim from KAIST. Today, I'm going to talk about PreSto, an in-storage data preprocessing system for training recommendation models. This work is done with my colleague Yoonjae Lee and Professor Min-Soo Liu. First, let me introduce the research scope of this work. Machine learning have demonstrated their effectiveness in a wide range of application domains, including chatbot, image recognition, and recommendation services. To ensure their high-quality services, hyperscalers dedicate significant efforts to the development and training of diverse ML models. Unlike ML serving, training algorithms are throughput-hungry workloads that favors high performance and throughput-optimized accelerators like TPUs, GPUs, or NPUs. Since these power-hungry accelerators account for a large portion of ML systems' operating expenses, maintaining high accelerator utilizations become critical for lowering the total cost of ownership. To sustain such high utility, it is important to continuously feed input data to accelerators. However, input data typically requires some form of pre-processing before training, including extraction and transformation of raw data. The key challenge of ML training pipeline is that the pre-processing stage potentially becomes a major bottleneck, restricting model training throughput and resulting in significant accelerator underutilization. In this work, we focus on data pre-processing stage of recommendation system, which from now on I will refer to as REXSys. Even though it is one of the most successfully deployed ML applications in today's data centers, its pre-processing stage still remains underexplored in our architecture community. Therefore, we explore a hardware-accelerated pre-processing system to enhance the overall throughput of REXSys training while keeping the system cost-effective. So you may be wondering what REXSys pre-processing system is. Let's look into how the overall REXSys training pipeline is structured. Numerous features derived from user interactions with ML serving engines are logged in a data warehouse in a tabular, row-oriented format. For model training, the target data set is sharded into multiple partitions, converted into a columnar format, and stored as independent files in the data center's storage system. And then, data preprocessing jobs feed the model training jobs by generating mini-batches from these columnar files. Let me explain the key steps of REXSys preprocessing in detail. First, the target low features are selectively extracted from a columnar file. In this example, target features are X and W. And then, the raw features are transformed to generate the new features X prime and W prime. Next, all elements of feature X prime and W prime are normalized. And finally, converted into training-ready tensors, which serve as an input mini-batch for the training job. There are numerous feature generation and normalization operations utilized in REXSys preprocessing. This table shows the representative operations that our work targets. Due to time constraints, I will not explain the details of these operations, and please refer to our paper for the comprehensive explanation. So far, we have covered the basics of REXSys preprocessing stage. Now, let's look into our baseline CPU-centric preprocessing system. Existing REXSys training pipeline adopts a disaggregated data preprocessing system where a pool of CPU cores are dedicated for data preprocessing. CPU-centric system employs producer-consumer model where a GPU training worker consumes a train-ready tensors produced by a CPU preprocessing worker. The key point is that the preprocessing for a single mini-batch is entirely executed by a single CPU core. Across 5 different datasets, we show end-to-end latency to preprocess a mini-batch using a single CPU worker. We developed 4 synthetic models to better represent the production workloads. Here, feature generation and normalizations are performance-limiting operations since the system relies on the limited computation power of a single CPU core. Then, you might wonder why the baseline system uses this approach. The reason is that the CPU-centric system is optimized for throughput rather than latency. Given that each file contains the complete feature set of different users, here feature X, Y, Z, and W, multiple CPU workers can produce mini-batches concurrently, achieving scalable preprocessing. Now, the remaining concern is to determine how many CPU cores are necessary to fully utilize GPU. We evaluated the number of CPU cores to fully utilize a GPU training node. We observed that the production scale models typically require several hundreds of CPU cores, resulting in substantial deployment cost and power consumption across the data center fleet. Now, let's come back to our research question. How could we design a high-performance and cost-effective Rexis preprocessing system? To answer this question, we developed PreSto, an in-stretch processing-based data preprocessing system for Rexis training. The key idea is to leverage the intra- and inter-feature parallelism inherent in Rexis preprocessing. This slide illustrates where feature generation and normalization exhibit such parallelism. Each element of a feature vector represents a user interaction with no data dependency across different users. Therefore, the operations can be conducted element-wise, exploiting intra-feature parallelism. Similarly, different features undergo independent operations, leveraging inter-feature parallelism. Given that the abundant feature parallelism in these operations is well suited for domain-specific accelerations, we propose to employ an hardware-accelerated computing for data preprocessing. However, an important decision still remains regarding where our accelerators should be deployed within the overall system architecture to ensure scalability and cost efficiency. To answer this question, we explore several possible design points. The first candidate is a scale-up server architecture that utilizes a PCI switch to collocate the pre-processing accelerators with the GPUs. However, this approach is limited in scalability because the aggregate pre-processing throughput is still bounded by the total number of accelerators in this server. Additionally, both the accelerator-side data preprocessing worker and the GPU-side training worker share the same PCI bus to communicate with the host, potentially creating a performance hotspot. To address these concerns, an alternative solution would be to reserve a disaggregated pool of preprocessing accelerators. This approach offers high scalability. However, like the baseline CPU-centric disaggregated system, it incurs substantial deployment cost and power consumption. Considering these challenges from the two systems, we adopt in-stretch processing architecture, or ISP architecture, in the storage system. Our proposed system leverages smart SSDs, which tightly couple a normal SSD with a lightweight FPGA device. We implement feature generation and normalization units on smart SSD to maximally exploit feature parallelism in Rexis preprocessing. First, to exploit intra-feature parallelism, each unit employs double buffering to overlap the fetching the next feature value with the computing the current one. Moreover, to exploit inter-feature parallelism, we deploy multiple processing elements dedicated to each feature. The key advantage of our ISP accelerator is its power efficiency. The local SSD to FPGA data transfer and FPGA-based acceleration operate within 25 watts power envelope, aligning with standard NVMe SSD power consumption. We have demonstrated our PreSto's efficiency, so now we show its high scalability with key steps of Rex's preprocessing. First, multiple columnar files are stored separately within the data center storage system. Since each file is partitioned by different users, there are no dependency on other files when generating a mini batches. So, all preprocessing operations can be locally conducted within a smart SSD. To sustain the throughput demand of the GPU training stage, multiple smart SSDs concurrently generate mini batches to beat the training node. Therefore, PreSto is a scalable ISP-based preprocessing system that can be seamlessly deployed within the power constraint of the baseline storage system, improving cost efficiency. Now, let's proceed to our evaluation methodology. We employed a multi-node hardware system, including a storage node with smart SSD, CPU nodes for CPU-centric preprocessing, and a GPU training node. Our software stack utilized TorchRec and TorchArrow. We set the baseline as the CPU-centric disaggregated system to demonstrate PreSto's effectiveness. For benchmark, we developed 4 synthetic Rex's datasets by scaling up the public dataset to better represent the production workloads. First, we show the breakdown of end-to-end preprocessing time to generate a single mini batch. At the right axis represents PreSto's speedup. Using our ISP acceleration to exploit intra and inter-feature parallelism, PreSto achieves an average 9.6 times reduction in end-to-end preprocessing time. Next, this figure compares the preprocessing throughput of the baseline and PreSto. As demonstrated, a single smart SSD device in PreSto consistently outperforms a single CPU node with 32 CPU cores highlighted in yellow. To prove the efficiency of our proposal, we measured the system-wide energy consumption and the total cost of ownership, considering the both capital and operating expenditures. As a result, PreSto achieves an average 11.3 times energy efficiency and 4.3 times cost efficiency improvement over the baseline system. To conclude, we have proposed PreSto, an in-stretch data preprocessing system for training recommendation models. Our work includes a detailed characterization on Rex's data preprocessing. We proposed an in-stretch preprocessing system that fully exploits inherent parallelism in Rex's preprocessing, demonstrating its efficiency over a CPU-centric system while ensuring scalability. Thank you for listening. I will be happy to answer any questions.
All right, please say your name and institution before you ask questions. Thank you.
Narsimha Reddy from Texas A&M. I have 2 questions. What is the API for doing processing near the storage? And the second question is, what happens if your file is sharded across multiple SSDs?
Can you repeat the second question again?
What happens if your file is distributed across multiple SSDs, let's say in a RAID system?
I see. For the API one, we use the Xilinx XRT runtime API to control the FPGA in the smart SSD device. And for the distributed storage system questions, for the data storage, we refer to the Meta's distributed file system, like Tectonic file systems. And in this paper, Meta stated that all blocks within the given partitioned columnar files are stored contiguously within a single storage device for the sake of simplicity. So this ensures that the single partitions will not be distributed across the multiple storage devices. So all preprocessing operations can be locally conducted within a smart SSD, single smart SSD card. So we can ensure the data locality, and that's why we can ensure the scalability of our system. Thank you for a great question.
All right, let's thank the speaker once again. All right, so our next paper is pSyncPIM, partially synchronous execution of sparse matrix operations for all bank PIM architectures. And our speaker is Taehyun Baek. Dr. Baek just received his PhD early this year at KAIST, where he worked with Professor Jae-hyuk Ha, and then he joined Samsung SDS as a senior engineer at the Technical Research Division. His research interests include hardware acceleration on sparse tensor kernels. Dr. Baek, you can take over.
Hi, this is Taehyun Baek, presenting pSyncPIM, partially synchronous execution of sparse matrix operations for all bank PIM architectures. First, this work focuses on sparse matrix kernel accelerations with under 1% densities. In this area, two major applications widely use sparse matrices. First, graph applications that use linear algebra as compute language. For graph processing, the graphs are transformed into sparse matrices for parallel computation. Another part is the numerical linear algebra apps that solve massive linear system equations. Several complex numerical analysis apps approximate some complex differential equations into linear systems, and the central part of these apps is solving the linear equations. Therefore, we started from the kernel analysis of these applications. From our analysis, the four significant kernels, sparse general matrix multiplication, sparse matrix vector multiplication, sparse triangular matrix vector solve, and vector element-wise operations are observed. Because the SPGMM kernel shows much more computation count than the memory input and output, this work does not focus on the SPGMM kernel. However, other than SPGMM, these three kernels are memory intensive, where the bottleneck comes from the memory bandwidth. Therefore, we're going to focus on these three kernels. To accelerate the memory intensive kernels with wider bandwidth, processing in memory technology was introduced. This technique utilizes multiple memory banks in the memory channel with a single memory command, which is different from one command, one bank activation on normal DRAMs. The PIM technology introduces additional processing units inside a memory chip attached to the banks. Each processing element reads and writes data using the same memory command from the host chip, but cannot communicate with each other. This approach is effective at dense matrix vector multiplication, which is simple and requires high memory bandwidth. While the current PIM products are effective on a dense matrix where all workloads can be distributed evenly. However, this approach cannot guarantee the functional correctness in the sparse matrix where the non-zero elements are distributed unevenly. In this example, the banks simultaneously access and compute the non-zero elements in the same position. However, in this case, there must be a bank that does not have any non-zero element on the position. Several previous academic works have proposed where the processing elements generate memory commands internally to overcome these limitations. These approaches suggest that internal data networks be used to balance the unevenness of workload distribution. However, these approaches change the timing of memory, which is unacceptable on the current DRAM and host chip communication. Therefore, we propose a partially synchronous execution scheme which maintains the synchronized all-bank execution scheme of the current industrial PIM products. Still, each processing unit diverges its execution path from the same host memory command. With this architecture, we propose a new memory mapping and acceleration scheme of SPMV and SPTRSV kernel. Let's start with the microarchitecture. In our processing element, there is a intersection and union scanner, vector scanner for computing the dense or sparse vectors, which is widely used in sparse matrix kernels. In addition, we introduce a sparse vector queue that stores 3 subqueues, which stores rows and columns and vectors. We designed a flexible instruction set architecture to support various algebras that are used in graph applications. To compute these unevenly distributed workloads for each processing unit element, we introduce a conditional execution and exit inside the execution path. The processing element executes an infinite loop of predicated instructions until the condition is met, which differs from the commercial PIMs that execute only finite loops. While the PIM instructions inside the loops are predicated, these instructions do not make any branches. While each processing element will perform a different number of loops inside, that depends on the number of non-zero elements, there must be an early exited processing elements inside the kernel execution because the number of non-zeros are differs. These early exited processing elements will usually activate and pre-charge with the same memory row for timing synchronization with other banks, but there's no data changes, which is a read and write command, for these already exited ones. With the previously described architecture, let's handle the actual kernels. In our computation scenarios, the input and output vectors that corresponding to the sparse matrices can be randomly accessed. Therefore, if these vectors are bigger than the size of memory rows, in this case, they will occupy multiple memory rows, and while these vectors are randomly accessed, the processing elements must traverse the entire memory rows for each loop, in this case, the 3 times, and which leads to this performance drop. Therefore, we have to limit the size of the submatrix for each bank, which is 1 kilobyte in our case. With this limitation, let's think about the actual SPMV execution. With naive distribution mechanism, the matrix should be divided into smaller submatrices for SPMV calculation, where each matrix have a few elements only. This results in memory bloating and lower performance on SPMV calculation. Therefore, our approach compresses the matrix for higher memory utilization and performance. First, we divide the matrix in row-wise manner, which is the number of rows fits in the memory row, and eliminates the columns that do not have any non-zero element. Then, this submatrix is mapped into each memory bank. So this scheme can reduce the memory bloating and the external memory traffic for input vector replication and output vector accumulation. With this compression technique, it is possible to make a simple load balancing technique. After the compression, it is possible to map each compressed submatrix into memory banks from the leftmost ones. While the compression makes the number of non-zero elements for each submatrix decreases from left to right, batching submatrix from left to right can handle the variety of number of non-zero elements for each submatrix, like this. Other than SPMV execution, we have to deal with the SPTRSV kernel. For the SPTRSV case, there are additional challenges for hardware implementation. While the SPTRSV is just a Gaussian elimination process for solving linear systems, this algorithm has a data dependency between rows and columns. Therefore, the kernel has a limited parallelism. To reduce the dependency problem, GPUs reorder the rows and batch process the independent rows simultaneously. But this approach is not scalable. In addition, there is a matrix size limit for processing in memory implementation, as I previously described. Therefore, we adopt a state-of-art block algorithm introduced in ICPP 2020. This approach divides the triangular matrix into 2 sub-triangular matrices and a square matrix that solves the upper triangular matrix first, then the square matrix next, and solves the other triangular matrix. While this approach can divide triangular matrices recursively as follows, it can accelerate any size of triangular sparse matrices by implementing just a unit size of SPTRSV kernel. For evaluation, we use the DRAM Sim3-based in-house simulator. For the baseline, we used a GeForce RTX 3080 GPU and the results from the Space A, which is a standalone self-memory command generating the sparse matrix processing in memory accelerator. For benchmarking, we use several multiple sparse matrices from graph applications and linear system solvers. We compare the performance of our architecture in both SPMV and SPTRSV kernels and the real-world benchmarks that is composed of several sparse matrix kernels. The result shows a substantial performance boost over RTX 3080, which is with a single chip scenario. pSyncPIM can outperform RTX 3080 with 2 times performance boost in SPMV kernel and 3.5 times boost on SPTRSV kernel. However, our architecture shows only 56% performance from SPACE. This comes from the inevitable overhead of our synchronized execution scheme, which is different from SPACE, where each bank can read and write asynchronously and has a data interconnect network inside the memory chip, which is undesirable. In addition, we tested the scalability of pSyncPIM in SPMV kernel with a 3 times chip scenario to match the external memory bandwidth of the RTX 3080. In this case, we could achieve 4.4 times performance boost over RTX 3080 and a 2.3 times scalability over a single chip scenario. In addition, we benchmarked several real-world applications, including graphs and linear systems. The details are shown in the paper. In conclusion, our approach maintains the current PIM communication standards supporting the sparse matrix kernels by the partially synchronous execution architecture. With several memory mapping and algorithmic techniques, it is possible to accelerate several sparse matrix memory-intensive applications, which can outperform the current high-end GPUs. Thank you for listening.
Hi, very interesting work. This is Mingyu Gao from Huang University. So I wonder, since I think you need to introduce some conditional execution to the hardware, so you need to make some hardware changes. Do you?
For the not only for the conditional exit, but the sparse matrix kernels are actually much more complex than the dense matrix kernels, so there must be multiple loops inside the processing memory kernels. But the current processing in memory does not support any multiple loop features. So I added several loop counters that can distinguish each loop to process the multiple loops, and because and there are, as you said, I added the condition checker inside the processing unit to check whether the condition is met or not.
Okay. So actually, yeah. my question is whether you can use like padding with zeros to avoid those conditional executions, so that you can make smaller hardware changes or fewer hardware changes there.
Our approach requires some substantial rework on the processing element. So I'm not targeting for the small changes for supporting all of the features. Yeah.
Okay, well, we can talk offline. Okay, thank you.
Yes. Hi, I'm Wang from Cornell University, and I have a question for you. Great talk, but I'm interested in how do you extract the data from the sparse matrix, say, stored in a file, to the sparse matrix itself. Do you assume that you do pre-processing in the specific format you want, or do you just do it on the fly where you do the explore when you runs?
And our assumption is that the sparse matrices were placed in the first time by the host chip in one time, because these applications uses the same matrix in the same without any modification, and executes a lot of loops with the same sparse matrix that does not change any position or data. So we excluded the overhead of implementing the sparse matrix into the memory mapping.
So you assume the matrix is being loaded in a somewhat dense format, say in continuous array beforehand, and then perform experiments on it. Is that correct?
The sparse matrices were initially loaded by the host processor, which is not simulated or implemented in my work.
Okay, so basically, it's not processed in sparse format. It's processed in the array format. Is that correct? Its sparse format matrix is usually compressed in that way that you don't have the whole grid loaded in your memory. So your processing memory assumes that each of the chunks you're working on is not in a sparse dense format. Is that correct?
Sorry, but due to the timing constraint, let's take this offline. Sorry for the. Yeah, you can just go and discuss these things in the offline.
Okay, great.
Yep. All right, so our next paper is NDSearch, accelerating graph-traversal-based approximate nearest neighbor search through near data processing. And the speaker is Wang, a PhD candidate in computer engineering in Duke ECE department, working with Professor Chen. His research interests include machine learning acceleration, near data processing for data-intensive application, and algorithm architecture co-design for deep learning systems. So please come
on. Where's my slides? Okay, sorry. Hello everyone, I'm Wang. I'm a PhD candidate at Duke University. Today I'm going to talk about our work in NDSearch, accelerating graph-traversal-based approximate nearest neighbor search through near data processing. So first I want to talk about the background about ANS, approximate nearest neighbor search. So before talking about ANS, I need to talk about NNS, nearest neighbor search. So for a database, especially a vector database nowadays, NNS uses a brute force scan method to find the exact nearest neighbors. So, however, approximate nearest neighbor search aims to find the approximate nearest neighbors in some applications where the approximate ones are acceptable. And there are multiple ANS algorithms. However, currently graph-traversal-based ANS is the most popular one because when scaling to billion-scale data, the speed is still great, and the speed is still fast, and the recall rate is better than other methods. And meanwhile, it has been commercially used by some companies in industry, like Amazon or Meituan. So this is I will next introduce workflow of ANS. ANS have two phases. The first phase is construction phases. It aims for building the graph. And the second phase is search phase. It search targets on the constructed graph. And this is also the phase our work focuses on. You can understand it's just like a breadth-first traversal search with some specialized conditions. And this phase have basically have three kernels: graph traversal, distance computation, and sorting. So here is an example about the traversal path. The red path is the traversal path in this construct graph. So for a given query, we firstly select V1 as the entry vertex, and then we traverse its neighbors V2, V3, V5. So, and then we do the distance computation. And if the computation is smaller than some threshold, it will be put into a candidate list. And we find the nearest neighbors of V1 as the next entry vertex in the next iteration. So we do this process iteratively until the termination condition is satisfied. So in this example, we end at vertex 12. And also, finally, we get the candidate list and do some sorting to find the top k nearest neighbors for each query. So that's basically workflow for that. And actually, for now, ANS have many important applications. First of all, I think everyone is familiar with is retrieval augmented generation for LLM. Actually, RAG takes input and retrieves a set of relevant supporting documents given a source, and given your original LLM input prompt, you can enhance the context by retrieval some related information in your local data set or local database. So another important application is the recommendation system. So far in industry, the recommendation usually have two stages. The first stage is called recording stage or retrieval stage. It is used ANS to retrieve some candidate to do the candidate generation. And the output of the first stage is then further put into the next stage ranking stage to get a more accurate results. So we did a general overhead analysis for some applications. For example, here it shows the two-stage recommendation sets here. We found that performing ANS during the retrieval or record stage, the first stage, averagely takes about 87% of the total execution latency. So that's why we want to accelerate ANS workload. So you may ask, why does ANS workload have a such large overhead? My answer is SSD I/O overhead. I did some profiling results around the HNSW and disk AN, which are two very well-known graph-traversal-based ANS algorithms now on the graphs constructed on 3 different data sets. So you can see that up to 75% overhead is taken by SSD I/O rate. So why? This is because the graph is usually too large to be stored in a CPU memory in a single node. So you need to redundantly and frequently fetch the partitioned graphs from the SSD. And meanwhile, the SSD I/O is very limited. So let's get deeper into the SSD I/O bandwidth. We did a roofline model here, and you can see the ANS workload is really bandwidth bound. So that's why we want to use in-storage computing to reduce the data movement and explore the internal bandwidth. As you can see here, when we improve the hardware bandwidth using our design, the ANS workload the performance of the ANS workload is significantly improved here. So you may ask how to design in-storage computing platforms, especially for ANS, like where to put the logic inside SSD. Actually, here is the structure of SSD here, and prior works gave some solutions and some choices. First one is you can implement the logic in the SSD controller. Second, you can implement a separate logic outside the controller, just near the DRAM, cache, and the SSD controller. And the third choice is that you can even implement some logic for each flash chip. So we can think, can we add somewhere else, but somewhere really makes sense. So before answering this question, I will show a characteristic study of our work, the data access pattern inside the SSD. So our first observation is that for a given query, the accessed vectors in the trace of one query are scattered in many pages. So this motivates us to improve the spatial data locality within pages. So our second observation is that 80% logic units are accessed when conducting the search phase of one batch of queries. Here, the logic unit is also LUN referred to as the LUN in the SSD. It is the minimal unit which can independently execute commands. So also following the sparse data access pattern, it inspires us to develop LUN-level accelerators and also meanwhile to improve the temporal locality for a batch of queries. So let's move to our design part. In the traditional architecture, I want to firstly speak about the traditional architecture. You need to fetch a lot of vectors from the SSD via the limited I/O I mentioned before to be processed with the queries. So you can see that this involves a lot of data movement here. So our method using the in-storage computing is that we want to make queries swim upstream and filter the stream from storage. So we just send the queries into the in-storage computing platform. And because compared to the volume of the vectors, the volumes of queries is very small, and only the in-storage computing platform just send back the generated candidates to outside the in-storage computing platform to be processed with the queries again. So with this core idea in mind, we propose our design, the NDSearch. Here is the overall NDSearch architecture. We offload the graph traversal and distance computation kernels to the in-storage platform. We call it SSD here. And we offload the sorting kernels to the FPGA. It uses Pythonic kernels. However, this is not the bottleneck of the workload and also not the focus of our work. So you can see, I'm sorry. Oops. you can see in the third SSD, in the in-story computing platform, we can have allocator and V-generator to do some scheduling. I will show later. And there is an array of SIN search in NAND components here. Each SIN have 2 LU accelerators when we go inside its architecture here. Actually, you can see that in each LU accelerator, we have the computation logic to do the distance computation. And also, we get a query queue to receive the queries that are allocated to that LU accelerator. Meanwhile, we also support the multi-LU search overflow to explore its LU and level parallelism. We modified the workload from multi-LU read, which is originally supported in the SSD, and also proposed third page command to support the overflow, which is also modified from the multi-LU read command here. So we also propose an efficient data layout for the NDSearch. This is because we found that the original data layout in the conventional architecture is not efficient for the in-story computing. This is mainly because they are redundant data access due to the granularity mismatch, because in the NS workload, the data access granularity is vector granularity, which is fine for cache-like granularity. However, in the in-story computing, the data access granularity is page granularity. So we customize LU CSR, which is customized for the LU accelerator. So I will not show details about it. You can see our paper for that because I don't have too much time for it. So I will talk more about the dynamic scheduling. As I mentioned, we also have 2 levels scheduling, the dynamic scheduling and also the statistical scheduling. The first technique about the dynamic scheduling is about the batch-wise dynamic allocating on V-generator and allocator. Actually, it aims to allocate the queries to its corresponding LU accelerators to be further processed. For example, here, using our LU and CSR format, we can get the neighbor IDs of query 1. This is vertex 3, 7, and 23. And their corresponding locations on the LUN is 113. So we allocate the query 1 to LUN1 and LUN3. We do the same thing for the query 2 and query 3. So in this way, one LU accelerator can process different and multiple queries within a batch. So we can improve the batch-wise temporal locality because we just need to load the data within the LU accelerators once, but to process multiple queries. Yeah, and we also have another dynamic scheduling technique. It's called speculative searching. Actually, it is based on the observation that the second order neighbors of the entries vertex in the current iteration are the potential vertices to be accessed in the next iteration. So our basic idea is just to let's do the allocating and searching process for the second orders in the current iteration in advance. So if there is any overlap between the second order neighbors in the current iteration and the neighbors that are in the next iteration, so the searching process can be accelerated. This is the basic idea of our speculative searching here. Yeah. Okay, let's move to the static scheduling. I want to talk more about the first one, the degree ascending breadth first traversal reordering here. Firstly, I want to give a definition about the metric we use here. It's called beta. Just forget about the math here. I can give you a straightforward understanding. You can understand beta as the average distance between a vertex and its neighbors. So in terms of address space. So the lower the beta is, the more closely a vertex will be stored with its neighbors. So you can have many methods to get a beta, just using some random reordering, just reorder the vertices in a computer graph. You can use this equation to get a beta here. But our goal is to minimize beta to make the low-order neighbors of each vertex in the graph stored as closely as possible. For example, we want more neighbors of a vertex to store in one page so we can improve the data locality in one page. So our intuition is that we want to, firstly, follow the nature of breadth-first search traversal path. And secondly, we want to give priority to reordering, to consecutively reordering the vertices with more neighbors. So in this way, we can have high probability of reordering more neighbors of a vertex together in one page. So in this way, we can improve the spatial locality with one page. Yep. And meanwhile, and using our method, we can see that we can get a lower beta here, so which means we can get a better data locality here. And also we follow the, we also do some further optimization about the multi-plane operation mapping to support the plane level parallelism within each LU and accelerator. But we also follow some restrictions of the original SSE spec, so we can do this in our way to further improve the graph traversal parallelism. So this is our evaluation part. For the benchmarks, I use HNSW with DSCAN and construct our graphs on the data sets we mentioned before. We compare our design to the CPU, GPU, and some near storage, in-storage accelerators. The results show that we can get significant throughout input over the CPU, GPU, and near storage accelerators like SmartSD and DStore. Also, we do an application study, found that actually the dynamic allocating part contributes significantly to the overall performance. And also, finally, we found that the SSD I/O is reduced to 6% from the 70% we showed before. So we can successfully reduce the SSD I/O here. Yep. Thank you so much for listening. I'm sorry.
Unfortunately, the time is up.
Yeah.
It's 3 minutes over, so let's take the discussions to the offline.
Yeah, sure.
All right, let's directly move on to the fourth paper. So our next paper is Enabling Efficient Large Recommendation Model Training with Near CXL Memory Processing. And then the speaker is Hwang Liao, a PhD candidate at Hwang University of Science and Technology, working with Professor Zheng. His current research interests include the techniques and applications of processing in and near memory.
Hello everyone. Good afternoon. My name is Liao and I'm currently a PhD candidate from Hwang University of Science and Technology. And today I'm very glad to be here to introduce our recent work on enabling efficient large language model training with near CXL memory processing. This is the outline of my talk, and I will begin by introducing the background and motivation. So as we know, recommendation models become more and more important and widely deployed in a range of applications such as the media, social network, e-commerce, and search engine. The deep learning-based recommendation model consists of a bottom FC layer that processes the dense features such as the user gender, age, location, and so on, and the embedding layer that processes the sparse features such as the user click history. And then both of the sparse and the dense features are further merged and processed by another top FC layer to give the final results. As the computer-intensive FC layer are well studied, we focus on the embedding layer in our work. The embedding layer exhibits large storage capacity, low compute density, and irregular memory access. It is treated as a typical memory-bounded application. To this end, existing solutions perform a CPU-GPU hybrid training model in which the embedding layers are stored in the main memory and processed by the CPU, while the DNA layers are resided in the GPU memory and are processed by GPU. However, as the embedding layer size expands faster than the memory capacity, the demand for increasingly substantial memory resource will soon surpass the particular limits of a single server with limited memory channels and slots, which make the embedding layers become more and more bottlenecked. So the scalability becomes very important for future scenarios of recommendation model training. Where the advent of the emerging open industry interconnection protocols, Compute Express Link, also known as CXL, brings a new chance for memory expansion and resource disaggregation. CXL is built upon the PCIe physical layer, and it contains 3 sub-protocols, CXL I/O, CXL cache, and CXL memory with support for different functionality, and it divides into 3 types of type 1 to 3 devices based on the equipped sub-protocols. All of the CXL devices, as well as the host, share a unified memory space, named as the host physical address. CXL treats memory sharing and pooling as one of its key features and become a promising solution for the memory expansion. To this end, we make a motivated evaluation of the recommendation model training with the naive CXL memory. In the baseline CPU-GPU system, the embedding tables are located in the main memory, and we replace it with the CXL memory, and other parts remains unchanged. However, we found that putting the embedding data into the CXL memory will significantly degrade our performance from 1.8 to 3.1 times. And the training latency of the embedding layer in both forward and backward stages significantly increase. As the latency of the recommendation model training is mainly dominated by the embedding layer, which are heavily dependent on the memory bandwidth. But unfortunately, the transmission bandwidth of CXL, for instance, the PCIe file with 8 lines, has only 32 gigabytes per second, which is even slower than a single channel of DDR5 memory. Although the memory bandwidth within the CXL memory pool can be as high as a local memory, but a large bandwidth gap between the CXL memory and the inner memory. Well, the effective system bandwidth is always limited to the shortest part, just like the bucket effect. Thereby, the bandwidth-limited CXL brings advanced performance impact for the memory bandwidth-sensitive applications. So, is there any potential solutions to solve this? The most direct one is to enhance the CXL memory transmission bandwidth, which directly increases the shortest board in the bucket. And another potential solution is to reduce the data transfer by applying the reduction operation in the memory, which no need to transfer all data, with only the reduced results are transferred over the CXL. For the embedding layer, the potential reduction in data transfer size can be 20 to 80 times, which can easily fill up the bandwidth gap. While applying the reduction in memory, the CXL bandwidth no longer becomes the system bottleneck, and we can further enhance the performance by increasing the internal memory bandwidth with the memory level parallelism. But however, the first potential solution is not on our consideration. This is because the CXL bandwidth is dangerous to the underlying PCIe, which is out of our control. Where the next two potential solutions align with the near memory processing technique, which motivated us for our work. So we next introduce our proposed solution of RE6L. So we built a scalable memory pool composed of our proposed RE6L devices, the number of which is expandable on demand. As the 6L switch network can support up to 4K nodes, we need the potential to suffice the need for future scenarios. RE6L device is designed as a large capacity memory expander featured with the near memory processing solution, featured with the near memory processing functionality, elevating the negative performance effects from the bandwidth-limited 6L bandwidth. Besides, as the 6L memory allows the memory access between 6L devices, we actualize it to support the efficient peer-to-peer communication between the RE6L devices and the DNA accelerator without going through the host. So inside the RE6L device, both the embedding forward and backward operations are performed in the unified hardware in a time-shared manner. This is because the forward and backward stages perform the same arithmetic operations and are sequentially executed in one chain iteration. To this end, all embedding layer operations are processed in the memory side, reducing the data movements over the bandwidth-limited 6L. Besides, we adopt the rank-level near memory processing, also increase the inner memory bandwidth. As we can see in the execution timeline comparison between the naive 6L memory and our proposed RE6L with near memory processing, we bypass the frequent data movements between the memory set and the host set. However, we also notice that the RE6L device remains idle when the training process is handled by the DNA accelerator, which makes it unutilized, especially for the workloads with large DNA layers. So, to this end, we propose to prefetch the forward result of next bench when the RE6L device is idle. But however, there is a read-after-write data dependency between the training benches. This is because the forward of each training bench always requires the updated data from the previous bench. Therefore, when we prefetch the forward results before the data in the previous bench are updated, it may cause errors for this embedding chain in contiguous bench due to the read-after-write dependency. So we solve it by adding a prefetch update stage in which the prefetched reduced vector are updated are updated before sending to the DNA accelerator. Note that in the hardware level, we only need to add some lightweight data forwarding in the near memory processing core. For more details about the hardware modification, you can refer to our paper. After adding the prefetch, the RISC-XL device utilization improves. But the DNA accelerator will stay idle until the embedding update and the prefetch update are finished, also making it underutilized. So we also propose to prioritize the urgent embeddings needed for the next bench. Specifically, we prioritize the execution of the prefetch update and postpone the embedding update with the next bench prefetch. This can achieved because we updated the prefetch data using the gradients instead of the updated embeddings. This is because the operations in the embedding reduction and the update complying with the commutative rule. The execution order of the update first or reduction order doesn't affect the final results. Therefore, we don't need to wait for the embeddings to be updated before the prefetch update. After applying the update scheduling, there are two benefits. First of all, the DNA accelerator begins process faster without waiting for all the embeddings are updated. And besides, new data reuse possibility exposes for these updated embedding vectors that are also gathered in the following bench. As shown in this example, we can directly using them to add, using the updated ones for the prefetch and further reduce memory access. And this updated scheduling also requires only lightweight hardware modification in the MM core. For more details, you can refer to our paper. And for the other designs, such as the address management and the data placement, you can refer to our paper for more details. Next, we evaluated the performance of the proposed RISC-XL against the state-of-the-art solutions. As we have low access to the real CXL products, we use a remote NUMA node in a dual circuit system to emulate the naive CXL memory as in some of the previous researches. Where for the RE6L, we built a cycle current simulator to evaluate its performance and effectiveness. These two tables show the configurations of the system and the evaluation workloads. Overall, RISC-XL outperforms the CPU-GPU baseline and the naive CXL memory solution by 9.4 times and 22.6 times on average, respectively. The RISC-XL-D, with only device process and without the rank-level near memory processing, also outperforms the naive CXL memory by 3.4 times due to its reduced data movements of the CXL link, where RISC-XL further enhances the performance by enabling the rank-level memory parallelism and higher internal memory bandwidth. Note that even with the idealized communication and the CXLI, performance improvements are marginal across all workloads, indicating that the successful mitigation of the advanced performance impact from the CXL. Besides, RISC-XL significantly reduced an average of 4.8 and 12.8 times energy consumption compared to the CPU-GPU baseline and the naive CXL memory system, respectively. This can be attributed to the shortened execution time and the reduced data movements. Generally, the significant performance speed up RE6L achieves directly translate into energy efficiency improvements. For more evaluation results such as the scalability and the sensitive study, please refer to our paper for more details. And in the end, let's give a brief conclusion. In this work, we first analyzed the CXL memory performance and demystify its adverse performance impact on the memory bandwidth sensitive load. Then we proposed RE6L, a CXL memory system with near memory processing support for the recommendation model training. RISC-XL leverages the abandoned memory provided by the CXL memory pool and the internal bandwidth provided by the near memory processing, enables on-demand memory expansion and eliminates the negative performance impact from the CXL from the limited bandwidth CXL. We also incorporate RISC-XL with two optimizations of the dependence-free prefetch and the updated scheduling, further maximize the hardware utilization and boost the system performance. And the evaluation results show that our system outperforms the state-of-the-art solutions. That's all. Thank you for your attention.
Any questions?
Hello, thank you. Great talk. I'm Yuan from UC I'm wondering why CXL is important here. What is different between this and like multi-sockets and near memory processing?
Can you speak again? I'm sorry.
Yeah. So why CXL is important here, and what is the difference between your work and normal near memory processing with multi-socket like memory?
Yes, CXL is important because that we want to keep the scalability for the future scenario that the data expand that the data amount expand faster. However, in the traditional near memory processing solutions, such as in the DIM, the memory channels and the slots in one single server is limited, so that the scalability of in the traditional server is it may be for short for the future scenario.
Okay, thank you.
Oh, thank you for your question.
All right, more questions? More questions? Let me ask one question then.
Okay.
So you have your discussion more focused on throughput more, but the CXL incurs like a latency over local memory. So what is the implications of that?
Oh yes, that's a good question. As the latency is another important metrics, but however, you know that in the scenario of the recommendation model training, that there is a lot of data movements between the memory and the processor. So I think the most important thing is that the bandwidth instead of the latency. This can also prove that there are some of the existing solutions that uses the high bandwidth HBM to increase the throughput. However, the HBM has a much longer latency than the conventional than the memory. So I think in the scenario of the recommendation model training, that the nanometer second level latency is not that important. Yes, thank you.
All right, thank you. Thanks. Okay. Thanks again. All right, so our last talk. So our last paper is exploiting similarity opportunity of emerging AI models on 3D hybrid bonding architecture. And our speaker is Yu-Bin Quinn, a PhD candidate at Tsinghua University. His research interests include computer architecture, energy efficient VLSI design, AI algorithm acceleration, and hardware software co-design.
Okay. Thanks for the introduction. Hello, everyone. I'm Yu-Bin Qin from Tsinghua University, and it's my honor to introduce our hybrid bonding accelerator. So this is the outline. I will first mainly discuss about the hybrid bonding techniques, including some basic concepts, some design considerations, and then I will introduce our accelerator design details. So let's get started. As we can see, the emerging AI models have greatly influenced our daily life. Back to the 1980s, AI can only be used to do gesture or number recognition, but today, the large language model helps us with language translation, image generation, even help us writing our academic work. But the increasing of the model size puts a huge pressure on the memory, especially on the bandwidth. So there is one possible solution to this issue, the hybrid bonding technique. The basic idea of hybrid bonding is to stack DRAM die on the top of the logic die and use Cooper pillar to connect two dies and use them as the data I/O. Because two dies are bonded together face-to-face, so the Cooper pillar can be placed anywhere around the chip. And this high I/O parallelism effectively improves the memory bandwidth. Compared with 2D or 2.5D DRAM, 3D DRAM increases the I/O density by 2 orders of magnitude, and the corresponding memory bandwidth is also increased by an order of magnitude. Also, the hybrid bonding does not require any phi to boost the frequency, so it only needs 0.024 picojoules per access. But the benefits of hybrid bonding actually is not a free lunch. We still need to take many design considerations or trade-offs when we make the designs. A typical one is that the DRAM banks are distributed in hybrid bonding technique. So if we try to merge all IOs from different banks, we have two choices. The first choice is to merge all IOs on the DRAM die, but the DRAM typically has only 3 metal layers, so the wiring introduces large area overhead. The second choice is to merge all the IOs on the logic die with crossbar. And the experiment showed that when concatenating IO from 256 megabytes banks, the crossbar takes over 10% of the area budget. So the conclusion is that to leverage the bandwidth benefits, we cannot merge all the data IOs, and the accelerator must accommodate distributed characteristics. So make a simple conclusion. The hybrid bonding technique has some attractive features like high bandwidth, low access power, but it also has overhead and requirements, such as data locality. The target application needs to fully take advantage of this hybrid bonding technique. We implement a hybrid bonding architecture to accelerate the vision AI models based on the analysis above. Since we find the frequency, DRAM access, and data distribution characteristics of vision models actually fits the working principle of hybrid bonding accelerator. And next, I will show the opportunities and challenges of the design. We notice one opportunity in the vision models. When we store data consecutively in the memory, the neighboring data tends to be similar because they have similar context information because of a 2D image. So we define a matrix to measure this kind of similarity between the neighboring data as shown in this equation. And lots of experiments are conducted to prove this phenomenon. For example, in VITB, the similarity ratio reaches 81.6% in the first layer, and in ResNet 50, it achieves an average similarity ratio over 60.9%. And when we shrink the size of the data cluster from 64 to 8 in terms of the block size, the stored data tends to contain more similar values. We conclude this phenomenon as clustering similarity effect, CSE. We know the similarity opportunity can be utilized to accelerate the computing. If two data are similar, we may only need to compute the difference between the data. And this difference can be very sparse and can be accelerated by any sparse engine design.
Talk 1 minute, please.
So we were, based on this thought, we introduced the architecture.
Okay, perfect. Thank you.
We try to implement a hybrid bonding-based CSE-aware accelerator, and there are 3 questions to be answered. The first question is how to find the similarity. The DRAM capacity is too large to exhaustively locate the similar data. A fast and energy-efficient approach is expected to detect the similar data pair. The second question is how to utilize the similarity. If we detect the similar data pair, we also need to fully take these benefits into consideration to accelerate the computing. And the third question is how to balance the similarity, because the distributed banks may face variable similarity scenario, so we need to have a workload balance mechanism to achieve the entire chip performance improvement. And this is the overall architecture of our work, which contains 4 DRAM and logic banks. The DRAM and logic die are connected with a Cooper pillar, and the design contains similarity detection, acceleration, and balance unit in the logic bank. I will introduce these parts in the following slides. Our idea of similarity detection is to use a hotspot to represent the similarity information of one region. The hotspot means it is a representative data that is similar to its neighboring data. We collect hotspots from the different regions to detect the similarity. Those hotspots are stored in the content addressable memory. We call it CAM. The CAM helps to search the matched hotspot within 1 clock cycle. And this is the detection workflow. When we read out data from the DRAM, it goes through the Cooper pillar and arrives at the CAM first. It will search for the matched hotspot. And if it successfully finds one, the hotspot is utilized to perform XOR operation with the following readout data. Because the hotspot and readout data are similar, so the XOR result becomes very much sparse. And the sparse result is further utilized to accelerate the computing. The XOR operation between the data and the hotspot are naturally produced 0 in the high order bits, so we use a scoreboard to track the non-zero data block, and only those valid blocks are computed in the PE line. We also pay attention to the PE level workload balance. The first data block in this example is 4-bit, so it takes 1 cycle to compute. And the second block also has 4-bit, so the PE also takes 1 cycle to compute. The workload imbalance will not affect the latency performance. And in the third block, it contains 2 cycles to compute when the PE workload is not even. Then the scoreboard will redistribute the workloads to available PE units. By skipping redundant 0, the PE is able to accelerate computing. For example, the PE2 and 3 will allocate half of its workload to PE0 and 1. And same story for the fourth block. It is 16-bit and takes 4 cycles to compute. And similarly, PE2 will find other 3 PEs to process the workload together. This balance mechanism will shorten the computing period from 8 to 4 cycles in this example. But the hybrid bonding DRAM has a very special feature that all the banks are distributed and independently controlled by the logical units, and each bank is unaware of its similarity ratio before the workload mapping. So some banks may have very high similarity ratio, but others may do not. So the bank-level similarity imbalance is a challenge for improving the chip-level performance. For this issue, we designed a bank-level balance technique in this work. When one of the logic banks completes its workload, it will send free signals to its neighboring banks, meaning that it is ready for other workloads. And so in the next step, the busy bank will check the content addressable memory to find the matched hotspot. And the hotspot is used to compress the workload, and only the non-zero data block is transferred, and the scoreboard tracks this information. So the previous has our design details, and next I will show our implementation. This is the hardware configuration of this work. The area of logic die and DRAM die are exactly matched. The logic die is implemented in 12 nanometer technology, and the DRAM die is in 17 nanometer technology. And the hybrid bonding DRAM achieves 16 terabytes per second of the bandwidth. This figure shows the layout of the proposed accelerator. Here, the PE array and SRAM buffer are the primary components, which occupy 37% and 26% of the chip area respectively, and followed by the DRAM I/O and the memory controller. And the other peripheral has only 7% of the area. And then I will show our evaluation and the results. We conduct some design space exploration work. With high bandwidth DRAM, the on-chip SRAM buffer can be shrunk to enlarge the size of the PE units. So we find the optimal SRAM size of each bank is to be 112 kilobytes, and the PE should be 0.96 teraflops, which is a very good point. Similarly, the CAM size is also fine-tuned according to its trade-off between the hit rate and the area. We analyze the hit rate curve with typical vision models and tasks, and we find that the 12 kilobytes of the CAM size is the rigid point for the hit rate curve, so it is selected as the CAM size. The overall performance is shown here. It has the performance improvement over conventional accelerators such as Tenstorrent or TPU-v3 is profiled in 2 steps. The first step is the benefits of the 3D hybrid bonding. And the second step is based on the 3D baseline. We leverage the data similarity for acceleration. And in the first step of the optimization, the 3D hybrid bonding accelerate achieves 6.72x and 2.34x of the throughput improvement over wormhole and TPU-v3. And the second step of the optimization, the similarity technique further improves the throughput by 1.21 times. And for energy efficiency, the 3D baseline achieves 3.49 and 2.89 times of the improvement over wormhole and TPU, and the data similarity further improves the 1.97 times of the energy efficiency. By stacking two wafers
You
together,
can see
the
us?
hybrid bonding
You
scheme
can see the
naturally achieves
presentation?
2.67 to 7.68 times of
Okay.
error efficiency improvement over 2D or 2.5D integration. And the similarity optimization further
can see
improves
the
it by 1.43 times.
The logo
So
of
it's
the
time for the conclusion. It is
ISCA.
the first hybrid bonding architecture for vision AI models, and we thoroughly analyzed the design considerations and overhead of hybrid bonding architecture. And we propose a synergic similarity-aware mechanism to accelerate the computing. And that's all for today's presentation. Thanks for your attention. And the leader of the work is also waiting on the line for the questions. Thank you.
Thank you. Yeah, go ahead.
Thank you. Thanks for a great talk, but I have a question, and in my understanding, it seems to apply approximation by reusing computation whose input is similar as current input. Is right? Okay.
Special features that fits not only fits a 3D hybrid bonding architecture, but also it has some special features can be utilized to accelerate computing. And in this work, we focus on the similarity. And we will compute the similarity. Actually, we compute the difference between similarity data. So the differences become sparser after the preprocessing. And the sparser data can be accelerated with some sparse engine proposing this work.
Oh, so if so, it should compromise accuracy degradation a little bit, I think. So I wonder in this aspect, how much accuracy degradation occurs with achieving this benefit you posted on the slide?
Yeah, so so you mean the question is the 3D architecture may compress because of some similarity technique? Is that right?
I'm asking about accuracy degradation aspect because it uses some kind of approximation. Is it right?
We do not have some approximation because we use the difference. The difference can be exactly matches the original compute after like the transforming the computing back to the original input. So we only need we only use the difference, but not some approximate technique. So it will not lose some accuracy.
I see. Thank you.
Yeah, thank you.
I think Shai from Google. I think I'd like to maybe repeat the point. How do you handle sparsity?
Thanks for the question. And sparsity is very important for our work. Actually, so we focus on the sparsity introduced by the similarity. So it means we will handle different types of the sparsity. So the activation may originally have some sparsity, but in this work, we try to produce more sparsity by focusing on the similarity between data. And the sparse engine is designed for this type of sparsity. And we use this type of the sparse engine to accelerate the sparse computing. So even the activation originally have some sparsity, we can efficiently process those data.
Okay, so this is maybe a more generic way to address sparsity?
Maybe you could say it's a more general accelerator, but I have to clarify that this work is mainly designed for a sparsity introduced by the similarity, but not a general sparsity accelerator.
Okay, thanks.
Yeah, thank you.
All right, let's thank the speaker and the lead author of the work. So again.
Yeah, thank you.
And with that, this concludes the session 4A. So there will be coffee break, and then posters will be presented on the hall. So let's take the remaining discussion to the hall. Thank you all. Thank you.